All right. Yeah, so we're tag teaming this. So I'm going to give a brief intro into, what our group is involved in with harmful algal blooms and hyperspectral ocean color data. And then I'm going to kick it over to Sachi, who's done much more analytical work with hyperspectral data. So anyway, so I'm Shelly Tomlinson, and this is Sachi. We work in the National Centers for Coastal Ocean Science. That's a branch within the National Ocean Service of NOAA, and we're located here in Silver Spring, Maryland. Go ahead, Sachi. It's fun. Oh, and I should clarify, this is really representing our whole branch and a lot of collaborators, but yeah, it'd take forever to mention all the people who've contributed to this work. So, okay, for those of you who aren't involved in harmful algal blooms or aren't familiar, I love this quote by the late Ted Smeda from URI. Basically, the salient criterion to use is defining whether a harmful species is in bloom, and the distinctive feature of such blooms lie not in the level of abundance, but whether its occurrence has harmful consequences. So, every workshop I've ever been to, people try to define what a harmful algal bloom is. From this criteria, it's something that causes a problem, a level of phytoplankton that causes a problem. That may be by producing a toxin. It may be an ecological disruptor where a high biomass bloom is causing hypoxia or fish kills, that sort of thing. Some of these blooms are detectable by satellite. Some of them are not. So some are toxic at very low concentrations. On the West Coast, they have a bloom former called Pseudonychia, which unfortunately is toxic at very low concentrations. So anyway, that's what we're talking about here in this talk. Next slide. So just a brief history as to how NOAA got involved in harmful algal bloom forecasting. In October of 1987, right around Halloween, a bloom of the red time former in Florida called Crinia brevis, which had been known in the Gulf of Mexico, way back in the 1800s. Anyway, it made landfall in Beaufort, North Carolina, where there happened to be a marine fisheries lab. So a colleague of ours, Dr. Pat Tester, was able to identify that it was Crinia brevis, and they were having massive fish kills. It's the first time it had shown up on the east coast of the US. Through looking at initially AVHRR data, so this is all SST on the right-hand side, they were able to find basically the bloom had started on the west coast of Florida. It came through the Straits of Florida and then was entrained into an eddy that ended up in the Gulf Stream, bringing it to North Carolina. So from there, later that year in November, the NESDIS, which is the Satellite Data Information System part of NOAA, started to provide SST data to determine the source of the bloom. So that's what those images are on the right. This caused fish kills, a lot of respiratory irritation on beaches, and as you see here in this picture, businesses had to close due to the toxins in the air. Next slide. So then we started adding winds as well to this satellite information. And what I already mentioned this, they figured out where the bloom came from in the Gulf Stream. And this later led to a program called NOAA's Coast Watch. This is some of you may be familiar with the Coast Watch program. It's run out of that office, NESDIS. There are nodes around the country that provide satellite data, training, and customized products to support folks around the country. So this is everything from ocean color to other satellite-derived products for ocean issues. Next slide. So my branch is actually our mission is dictated by an authorization in Congress called the HABARCA, which is the HAB and Hypoxia Research Control Act. So we are responsible for delivering near real-time forecasting products on the intensity, severity, location, and risk of HABs around the country, to include the Great Lakes. So we've developed a monitoring and forecasting system, which is national in scope. We have individual forecast products, some of which include models, others are really driven by the satellite imagery. that are to understand the drivers for HABs, including physical, atmospheric, and environmental conditions, which cause them to occur, when and where they occur. These products are delivered locally and serve as a decision support tool to provide early warning on these regional blooms. So each harmful algal bloom system is different. The species occurring, their ecology is different. So, you know, when we go into a new area, we really have to understand everything about, you know, the oceanography, the ecology, et cetera, of that bloom. I want to put one caveat, because I think I've heard a couple times about the HAB algorithms, and there's no such thing. Basically, our forecasts and the satellite imagery cannot detect a species at a species level. They can, you know, only tell you that there's a lot of stuff in the water, and we can only see things that are visible from the surface. So we generally cannot detect blooms that occur at really low concentrations where they start to impact shellfish. So regulatory limits in shellfish are at really low phytoplankton concentrations. Next slide. So here's just kind of a visual of where we have forecasting systems. There are several operational systems in the Gulf of Maine for a species called Alexandrium. That one causes paralytic shellfish poisoning. Then on the West Coast, there are forecast systems for toxic pseudonychia, which causes domoic acid poisoning or amnesic shellfish poisoning. We also have the forecast system for the Carinia brevis blooms that I mentioned that occur in the Gulf of Mexico and very less often on the east coast of Florida. And then we have a research model that's running right now in the Chesapeake Bay, really in the lower portion of the Chesapeake Bay for Margolefidinium polycrocoides. That's a bloom that affects larval shellfish and fisheries. So there's also a group at AOML that is running a demonstration forecast for sargassum. And I should mention, these are both operational within my office or with collaborators in other regions. A lot of the IU's integrated ocean observing systems are involved in running some of these forecasts, as well as Coast Watch. Next slide. Okay, so now getting into satellites. I already mentioned that we can't see low levels of harmful algae. So what we're predicting, or what we're visualizing with the satellite imagery, is a level at which the blooms have discolored the water. And this is an example of some of the products that we're using in Chesapeake Bay and in coastal HABs. As you can see on the left, I should mention, these are all from the Ocean Land Color Imager from Sentinel-3. So they are a 300-meter pixel resolution image that are provided daily from the European, from EUMETSAT and ESA. So basically, some of the products that we're providing, on the left, you see a true color image. True color is great to get an idea of, you know, sort of the rough color of the surface, but it's really hard to tease out what is happening. I think Ryan in the intro slide showed how the color of water changes if you add sediment and you add phytoplankton in coastal areas, and especially some of these estuaries like Chesapeake Bay. It's hard to tease out those various characteristics. So we tend to use derived products. And so I'm just going to walk through a couple of them real quickly. The second product, number one here, is the chlorophyll A. We're using a red edge chlorophyll in coastal areas. The traditional blue to green ratio algorithms that, a lot of the operational global chlorophyll products that are provided don't do a good job in coastal regions. So there's paper by Wynn et al. Shows the validation of this product in Chesapeake Bay, so you can look at that if you're interested. However, offshore, the traditional OC4 type algorithms do a better job. So we have a switch to low chlorophyll waters to that algorithm. So the second is a red band difference algorithm. This tends to pick up really high biomass blooms that are fluorescing brightly. So what you're seeing here is a relative abundance of the fluorescent signature of the phytoplankton. And in most cases, these really dense red patches are tied to dinoflagellates. And the reason for that is dinoflagellates can swim to the surface and really concentrate at the surface. And so when they are there, they bloom big and they're easier to pick up with this fluorescent signature. You can pick up diatoms, but they're going to be at a more low level of fluorescence, mainly because they can't swim, and so they're sort of mixed in the water column. And then for cyanobacteria, we have an operational algorithm called the Cyanobacteria Index, and this is used in our forecast system up in the Great Lakes. It's also the algorithm that's provided by the Cyan project that I think Ryan or Jeremy mentioned yesterday. So this is a product that's provided for all lakes around the country that are about 1 kilometer wide. Next slide. So now I'm going to turn it over to Sachi to talk about some work he's been doing with detecting cyanobacteria and separating them with hyperspectral.
Thank you, Shelly.
Sure.
So by this time, we have established that cyanohab is a critical water quality issue, and therefore they must be monitored. So over the pre-PACE era, before launch of PACE, traditionally, we as a research community have used multispectral sensors like MERIS and ULCI to identify cyanobacteria. For example, in this image you see here, it's a cyanobacteria index from Western Lake Erie. You see the detected cyanobloom. But we cannot say what kind of cyanobacteria, what genus of cyanobacteria is present in the lake. So fortunately, with hyperspectral sensors that collect rich spectral information and capture subtle spectral differences among phytoplankton types, we can use that information to identify those cyanobacteria genera. And if we can do that, we can map the toxicity and risk profile of certain cyanohabs. So that would be a valuable information. So with that motivation, here are our objectives. So we intend to develop a method to discriminate, to identify cyanobacteria genera from hyperspectral remote sensing deflections data, and then I independently validate the method and highlight challenges and opportunities of applying the same method to PACE OCI data. So but there are challenges. So to do that, we need genus-specific IOPs, AOPs, or the backscattering and absorption profile of those algae to develop bioptical models. And generating this AOP, IOP for lab culture is extremely challenging, if not impossible. And when we consider mixed blooms, so generating mixed species dataset is even more challenging. So how can we address this challenge? So there are several ways, but in this study, we used a lab and data-driven approach to address that question. So first, we need a spectral library like a fingerprint database, and we can generate that library in lab. Next, we build a model. Then we validate the model in the field with a hyperspectral image collected by a UAV platform and possibly identify what kind of cyanobacteria is present in the water. And we selected a gathering pond southeast of Milford Lake, Kansas, as our field study. So once we do that, we can take that algorithm to PACE OCI and identify cyanobacteria genus in Western Lake Erie. So first step is creating the reference library. So we monocultured 15 unique species of cyanobacteria in the lab, and the hyperspectral images with 235 channels in the visible NIR wavelength range were captured using resonant camera. And in total, 150 images were captured from all species in 3 combinations and in 3 concentration at 3 optical density combinations. So then the image means were extracted to present the unique species. Then we further generated mixed spectra with several species combined by mixing several species by linearly mixing up to 3 different species to generate that mixed spectra that mimics the mixed bloom situation in the field. So once we have the mixed library, we can smooth and normalize the signatures and collect the second derivatives which are used for the model. So here are the pure reflectance signature in our library. It appears most of the genera, if you look at it, it looks like most of the genera look very similar within the visible range, visible to NI range. And other than two species, those are the pseudoanabina, if you see the red dotted line and the green line on the top, other than that, everything looks the same. But when you look at the second derivatives, then we look at, we see differences, we notice differences. And here the primary idea is these derivative shapes are unique to this cyanobacteria genera, and probably we can use that to identify them through the algorithm. So here is another example of how second derivatives enhances the spectral separability. For that, we are using NS3 score, which is normalized spectral separability score. So the plot, what you are seeing here is a heat map, and it's like a correlation matrix. It can be interpreted as a correlation matrix. For example, here, the higher scores are color-coded warm colors. And if it has a higher score, then those two species are more separable, or they're dissimilar among themselves. For example, Dolichos formum is not anything like Pseudoanabina, whereas wherever we see the darker tones, those are very similar. So this NS3 score was calculated from remote sensing reflectance data, but when you do the same thing with second derivative, notice how it lights up. And it looks much warmer, means the dissimilarity scores are larger. So our first approach was to develop a classifier using the similarity index, or more formally the cosine similarity. It's a simple idea, but quite effective. The value of this measure varies from 0 to 1, 0 being no similarity at all, and 1 being perfectly similar. And in practice, we can find the similarity scores by matching an unknown with the signatures and classify based on the highest similarity scores. So we consider this as a baseline model. So as an alternative approach, we developed a machine learning classifier using fully connected deep neural net. So you see the figure here. Here is an example figure, and it shows the network with the two hidden layers and one output layer with multiple outputs, because we frame the problem as a multi-level classification problem. What does that mean? For every pixel in our data, it will have multiple predictions or multiple probabilities based on what species is present. So the network is a fully connected deep neural net, as I said, and it uses second derivative. And based on the spectral configuration, we have 8 spectral configurations using different wavelength ranges within the visible range. And using a sigmoid activation function, we're converting all those probabilities to multiple classes. And for independent testing, we trained the model with 80% of the data and validated on the leftover 20%, or tested with 20% of the data. So 5 replicates were trained so that we can capture the variability of the prediction. So for completeness, let's also look at what accuracy metrics we're using to validate our model. For multi-level prediction, the ideal metric is exact match ratio. So what it does is it checks for exact class prediction for each instance and scores. But if one prediction is wrong, then it records as completely inaccurate. So we thought this metric was too strict. We wanted a metric that could reward the classifier for partial correct predictions as well. So here are the metrics we can use: the precision, recall, and F1 score. So the precision is the metric that checks the fraction of predictions that are true. And if we have more false positives, we will have precision will go down. Similarly, recall checks what fraction of the true class are correctly predicted by the classifier. It means if we have more false negative, then recall goes down. And F1 score takes those two metrics and basically harmonic mean of those two and provides a balanced view of both precision and recall. So now that we have established the method and accuracy metrics, we can collect the US data and validate our model. So we use a resonant camera on a quadcopter platform and use the same data processing pipeline to generate the second derivative that will fit into the model. So here is the experiment design in the field. So you see the position of those mesochas, what you see in the figure. So the idea of this is so that the water doesn't move, and we can sample the algae and look at under microscope and get the cell count information, and we can tie that back to the UAV observations. So that is the main idea of using a mesocosm in this case. And also you see those GCP panels or ground control point panels just for georegistration of the image. And we also collected concurrent water samples for microscopic identification and cell count analysis of those water samples. And you see the RGB image from the UAV flight data. So what was blooming here in the water? So data from microscopy confirmed that there was a moderate bloom with total cell count varying from 320,000 to 650,000 cells per ml. And more than 88% of the total biomass was from cyanobacteria. So cyanobacteria dominated the community composition in this case. And next we can look at the percent contribution of cyanobacteria species. And those numbers tell us that it was a mixed bloom, genus dominance wise, it's a mixed bloom. And not a single species exceeded 50% of the biomass. And the dominant species are Pseudoanabina, Dolichospermum, Microcystis, and other few species like Planktothrix, Planktolimbia, and Aphanocapsa. So here I would highlight that we didn't have Planktothrix and Planktolimbia in our library, so the model is not going to capture that. So we have all the information. We collected the data. We have the field data for validation. So this is the algorithm validation. And we applied the spectral similarity classifier to the UAV data. And we detected Dolichospermum and Microcystis, Pseudoanabina. Dolichospermum and Microcystis from the image. So just to orient you to the figure here, what we're seeing here is a heat map of this metrics, precision, recall, and F1 score. And as you notice, we're getting high F1 scores for Dolichospermum and Microcystis, and the model missed picking Pseudoanabina. This could be due to a low fraction of Pseudoanabina in the total cyanobacteria biomass, which is found to be about less than 12%. So the next one is the US validation using the neural network classifier. So as I mentioned earlier, we trained several models with different spectral configurations. And these two figures, compare their performance and rank those models. So the left one is a precision recall curve. The x-axis is precision, and y-axis shows the recall from the models. And there are a total of 14 models. And we, due to the interest of time, we will just focus on the top model, what we have here. And this figure shows us that the top, most of the models are We use, by the way, the rate, the no PCA any PCA, and those are the and is in the interest. I mean, what we have here is the pace model. Um, so here, what we're doing is we, while the model training, we left we leave out 20% of the data. So that is being used. See, the prediction accuracy was close to 100% here. So now you may be wondering what happens if we use some sort of dimensionality reduction to the hyperspectral data. And we did that experiment. We ran the experiment, and what I found out is the average F1 score reduces when we use dimensionality reduction. So the figure here shows all those models we tried, and their corresponding PCA and no PCA model configuration. And as you notice, average F1 score for PCA was 0.78, and average F1 score with PCA was 0.56. So here, when we use PCA-based dimensionality reduction, we are losing 20% of the model accuracy. So we also experimented how noise could affect the prediction accuracy. So in this figure, we simulated that noise experiment. So just to give you a little bit information about the data, what we used here. So in this case, we're using the lab test set, the mixed signature data, what we generated from the laboratory data set, and using the noise simulation based on the OCI-based OCI literature-based noise modeling. What we found out is model performance decreases with noise, that is expected. So in this figure, each line is a model, and y-axis shows the SNR scales. And as you notice, there is no noise or infinite SNR. So that means that is our pure lab data without any noise. And SNR scale of 1 indicates it has noise equivalent to our OCI noise. Whatever the OCI, base OCI will have or expected to have. So it is the same noise. And when SNR scale of 0.5, then the noise doubles. And with 0.25, noise is 4 times. And with 0.2, noise is 5 times of OCI SNR. So as you notice, the average F1 score from all models, when we average out all those models, then at no noise, the score is 99%. So the models are very accurate. And with one SNR or with OCI level noise, so the accuracy goes down to 87%. So that is 12% reduction in accuracy. And with 0.5 or double the noise, the accuracy comes down to 67%, which is a 32% reduction in noise. So then after we're done with the US data, we took the PACE-specific model to evaluate with PACE OCI data. So in this case, the PACE-specific model, it was trained by lab data, as I discussed, and it included spectral features from 510 to 670 nanometer wavelength range. And those spectral features are those second derivatives. And it skips the bands from 590 to 610 because of the data gap, what you might already know because of the focal plane overlap. And the model was not trained with new PACE data. the data from PACE as such, but only validated with PACE data. So then it was applied to PACE surface reflectance, and we applied the same data pre-processing pipeline. So that is smoothing, normalization, and calculation of second derivatives. And model was trained with mixed spectral reflectance data, and we don't have any field data to validate those PACE images or classified images of PACE. But we will do qualitative interpretation of the prediction classes, as well as we will just assess based on the information what is available in the literature. So here is the Western Lake Erie example from August 24th, 2024. And these are preliminary results. So what do you see here? The left image is PACE CI cyano, which is the multispectral algorithm that is typically applied to Maris and Olchi. So in this case, we we just use those those Olchi bands from OCI and calculated the PACE CI cyano, and that detects or that shows the presence of the bloom, and also it quantifies the biomass of the bloom, but it doesn't tell what type of cyanobacteria. But the middle image is the cyanobacteria gender prediction from the algorithm, and what we are seeing here is the classes, the cyanobacteria predictions with highest probability values from the classifier. And the last image is the cyanobacteria genera with second highest probability from the classifier. So we are picking, with the highest probability, we are picking Microcystis and Pseudonabina primarily. And in the second case, with the second highest probability classes are again Microcystis, aeruginosa, and Aphanigemenon. And so although we don't have field data, but what it is commonly known or widely known is Western Lake Erie bloom in summertime. These are predominantly dominated by Microcystis. So that whatever prediction we're making here, it matches with our knowledge as well as the literature value, literature information. And also some literature says that Aphanigemenon is also present or can co-occur with Microcystis. So what these predictions tell? The predictions tell that at a given pixel, two genera from the middle and right side image are present. And what it doesn't tell is their relative proportion. So highest probability in the middle image, those two classes have highest probability. It doesn't mean they have the dominance or they occur in larger quantity as compared to the second highest probability. It just confirms those species or those genera are present in the water. So this is the same case after 2 days. So August 26, 2024, and it's the same bloom, and the highest probability classes are Microcystis and Microcystis aeruginosa and Microcystis sp and Pseudonabina, but primarily Microcystis sp and Pseudonabina in this case. And the second classes are Microcystis and some Anathesia. So what happens is, based on literature information, Anathesia can co-occur with Microcystis along the edges of the bloom where the biomass is in low concentration. So the predictions match with what we'd learned from the literature. And after 4 days, it was the 4 days of the bloom, and it's on August 30th, 2024. And here we are predominantly picking Microcystis sp and also Anathesia. So here, one thing to notice here in these cases is the spatial consistency of the predictions. So we see wherever we predict microcystis or pseudoangina, then there is spatial consistency in the image. So that tells us that these predictions are not random. So here are the few take-home points from this study. First of all, the baseline model. This is our spectral similarity model based on spectral similarity index. The model detected the dominant species when the signature was present in the library, otherwise it didn't. Just like the Planktothrix was present, but it was not in our library. And detection accuracy from the machine learning approach was near 100% in the lab data, as we noticed. And overall, machine learning-based classifier performed better than the baseline model. Then we saw how the dimensionality reduction, PCA-based dimensionality reduction, reduced the model accuracy up to 22%. And a typical OCI sensor noise reduces model accuracy up to 12%. And we applied the same algorithm to paste data, and the model was able to detect those cyanobacteria genera in the paste image in the Western Lake area. So moving forward, so the next step is the validation of the rigorous field validation of skill assessment of this classifier using field observations, and also based on that field model assessment or skill assessment, probably there could be model fine tuning. So that is the next step. Then we can extend to other coastal and estuarine hubs as well. So the current study primarily focused on, I should say, only focused on cyanobacteria types, but the same idea can be extended to other coastal blooms as well, non-cyanobacteria like any other coastal and estuarine hubs, primarily in Chesapeake Bay. And we can also use or extend this algorithm to other in situ and airborne hyperspectral sensors. For example, we have Hub Mapper, which is a radiometer on a UAV platform, or it can also be operated from either a ship or handheld device. So it can be the algorithm can be applied to that, and any other imaging hyperspectral sensors, including in-water radiometer or radiometry data as well. So with that, I would thank Katie, Rick, and Andrew from our group. Big shout out to Katie for setting up or generating the spectral library, and Molly from U.S. Army Corps of Engineer, Laura from EPA, and Dale from University of Florida, who were part of the field campaign and the design of the experiment, the field part of the experiment design team. So with that, thank you very much. And if there are any questions, we can take those questions.